We are happy to have today Ursula Mueller-Harknett, professor of physics. She earned his diploma in mathematics from the Free University Berlin, Germany, and a doctorate in mathematics from the University of Bremen. Before coming to Texas A&M, she taught at the University of Bremen, where she completed her habilitation and held visiting positions in Germany, Canada, and Arizona. Her research areas include regression, stochastic process models, non-parametrics, semi-parametric inference, asymptotic theory, and missing data. She has served on several departmental and college committees here at Texas A&M, Department of Statistics. In 2015, the Association of Former Students honored Dr. Miller with a Distinguished Achievement Award for teaching. Dr. Miller is a member of editorial boards of Annals of the Institute of Mathematical Statistics, Sankaya A, Statistics and Probability Letters, and JASA. She officially retired from Texas A&M University in 2018, in May of 2018, and was named the Professor Emerita of Statistics in August 2018. So her affiliation is quite long in Texas. By chance, a couple years ago, I found one paper written by Dr. Miller. It is about the stochastic resonance paper and model that essentially you have the thresholds. The data is sub-threshold coming your way, but if you noise it and put some noise, the stochastic resonance gives the boost and you can sense the sync. And that was amazingly interesting. So she has several papers in that area that I really admire. So today, she's going to talk about estimating the error distribution in semi-parametric plots. Do we have the...
I'm working on it. It's not ready right now.
It is not ready. Yeah. So Ushi, can you speak as loud as you can?
Okay. But I used to teach in this room.
So let's
Everybody for coming. I know their busy schedule and they're already talking to departments. So everybody has a very nice introduction. Can you hear me? Right. I learned that I was teaching the different systems as a software. So I had to spend it was a bit unpleasant because when you're trying to look at my slide, I have to turn around. Let's see how it works. We can make a test first. When I stand here, can you hear me? Everybody? Right. Then I stay here. Okay, I'm talking about, okay, actually I suggested 3 talks for this seminar, and Ronnie said they all sound interesting, so I decided to go for this one, which is something, I think one of my most important strands of research. And it's about estimating the error distribution in semi-parametric models. So I will simply review several papers on the topic. In particular, those are the most important one and the ones I find most interesting one. So I skipped many of them. So I hope it's interesting, but it will be very theoretical. So that's a warning. Not too theoretical. I don't bother you with proofs. Where do I have to point this? Okay, I think
switch on.
This one. Okay, so this one is with my, most of it is joint work with Anton Schick and Wolfgang Wesenmeier. Well, when you read MSW, it's easy. Right? We all have been here visiting. Anton even worked there for what is it called? Sabbatical, for sabbatical an entire semester. So he's in Binghamton, in Binghamton, and Wolfgang is in Cologne in Germany. Wrong direction. And the last part of this research is with Anton Schick and Gerhard Paul. Gerhard Paul is now Professor Emeritus in East Lansing, in Michigan State University in East Lansing.
Okay, so I hope it's interesting enough. Don't stop me if you have questions. I have to get used to the direction. Okay, so mainly it's about a regression. So I have an arbitrary regression model written down there. R of x is a regression function. And I assume that the covariates x and the errors epsilon are independent and the errors have mean 0. Then you can also add a variance function, for example. Then it's a heteroscedastic model. So with the independence and assumption, it's a homoscedastic model. And statistical analysis is typically based on independent copies of a pair x, y. And in parametric regression, we know R up to a Euclidean parameter theta, then it's just a function of x and theta, for example, a linear regression model. In non-parametric regression, we assume that R is smooth and unknown, but otherwise unknown. So we know that there are certain derivatives or some Hölder or Lipschitz conditions. In semi-parametric regression, we know R up to a finite dimensional parameter theta and an infinite dimensional parameter gamma. So then, triple R is a function of x, theta, and gamma. Okay, some examples are the partially linear model. Here we have the linear part and the non-parametric part. A single index model. And here we have actually a linear model, but it's a single index function, a non-parametric function that needs to be estimated, or a single index random coefficient model, where we have some, okay, where the parameter is simply modeled by the coefficient is simply modeled by a single index. Just some examples. If you read my papers, you find all these things. Which direction? Yeah. Okay, our goal is estimation of the error distribution. In particular, estimation of the error distribution function F. And now I come back to stochastic resonance, because what I was primarily interested when I started working on these things was estimating the error variance in regression. That came when I worked on stochastic resonance, because there's an optimal noise level when you estimate a regression function. And stochastic resonance is actually a very interesting thing. It comes from the ice ages. That's when the thermos point, the recurrence of ice ages become periodic with a certain periodicity. You can explain it by the orbital eccentricity of the Earth. If it's a thickness of 2b, so there must be additional noise shifted from one state to the other. So that's very interesting. And I did something with non-parametric. There was actually a non-parametric regression function which you can only estimate a time point. You only say which time point is special. Then you use these data for different strategies. For the homework problem, the project statistics. Okay, so that's how it came into rolling, and a lot of papers appeared. Okay, so what we are mainly interested in later was the estimation of the error distribution function with a rate square root of n based on by a residual based empirical distribution function. Good. Okay, the problem comes in here. You have R hat. If it's non-parametric or semi-parametric, you usually or often don't have the root square root of n. You have it in parametric regression, but not always. So when we want to estimate the error distribution function, that will be estimated the square root of the root n rate. And I do efficiency. If possible, we want to estimate the error distribution function efficiently. Okay, and this distribution function, the estimated one, we have based on residuals. It's the residual based empirical distribution function. This can be used for statistical inference, which does not require a statistical model for the error distribution, which is quite nice. And an example of the simplest statistic would be the Kolmogorov-Smirnov goodness of fit test statistic based on the statistics, so primo, and here is the difference between the the residual phase empirical distribution function in a non-parametric regression model where we have no model, and minus some different one where we construct the residual here with parametric regression function, for example, a semi-parametric one. Okay, so there you can do lack of fit tests or goodness of fit tests. I don't know what is exactly the difference between lack of fit and goodness of fit. I think the lack of fit is a bit more pessimistic and goodness of fit is more optimistic. Okay, so you can, for example, test the parametric form of a regression function, or you can test for additivity by using this approach, or for linearity. When you here have the non-parametric part, stop since no, fix the wrong button. Sorry. Okay, here you have the non-parametric part, a partly linear model, and you can test whether the non-parametric part is a constant. That's testing for linearity, or just simply test whether the error distribution follows a certain parametric model. So we call it F0, for example, or we can test for normal errors. Okay, and our fundamental uniform expansion is here. That's what we derive for several models. Okay. And the expansion says it's a uniform expansion because that's the supremum. The supremum of the residual phase empirical distribution function and the regular one based on the true errors that can be approximated by the density f of t times the average of the errors. And here we have the desired rate little op of 1 over square root of n. It's a very nice and very important result. Which means the one residual based one differs from the one based on true errors by an additive expression up to this little remainder. Okay, now we rewrite it and I a sip of water. Yes.
Sorry, what are you doing to wait for X? What's the The little f is okay. We want to estimate the error distribution function with this capital R. Is this a true value? True density? Yes, a true density. What are you asking?
I guess that they have the microphone.
You have the microphone?
Yes. Yes, please. Thank you.
Will I go ahead nevertheless? Okay. Okay, we wanted to rewrite it. We simply add plus minus the unknown error distribution function. Rearrange it. This one is simply different. So we have an approximation of the difference between the residual phase and the unknown error distribution, so the empirical. It's not the one they're interested in. We can approximate it by this.
Okay.
There is a sum of independent random variables, which is the interest. This is all you need.
Yeah. Sorry about that.
Where my life
I think the
keeps
first time
snapping my
the
head.
top of mine gets taken. Recorded. Okay, this term is now Cn and
The rate of O is the stuff when goes to 0.
Should be running.
Should be that one right there. Yeah.
Should be a USB.
Means square root of n times this.
Can you expand that?
This is important. This is important. It comes back and back. Can you get to the next slide? For me?
Yes.
Thank you.
Mhm. It's the 1, 2. That's 1, 2.
Okay. Actually, the efficient influence. Did you test it? Hello? Hello? Everybody on Zoom can hear me, but it doesn't help me here. I don't think that anybody here is on Zoom. We are recording. Is it good like that? Okay. Okay, I stay here for now. Okay, this is important. It's now the efficient influence function. Can I go to the next slide, please? Okay, let's look back. Okay, so I started with stochastic resonance. We want to estimate the error variance in non-parametric regression, and that was our first paper about it. So we were interested in the error variance, but we looked at it a little bit more general. We looked at a function, expected value of h of epsilon. So the error variance, because we have mean zero errors, is simply expected value epsilon squared. So if we can do it for a general h, why might not do it for a general h? And then we discussed the error variance as a special case. Okay, and we have shown that this is now the efficient influence function for estimating expected value of h of epsilon. So we have, yeah. And here we have this core function for location coming in minus f prime over f. And as a special case, we obtained the empirical distribution function. If h of epsilon is the indicator that epsilon is less or equal than t, then the expected value is, of course, the f of t, the capital F of t. So for this special case, we have the expansion we know. So it's the first time we had this expansion. Thank you. I think it's to go back. It's a question I'm asking it, but I don't want to show the answer. No, it's fine here. Then we have the, just don't go too fast, too far. Okay, let's go back to the error variance. In that case, it's quite interesting because the last term here, it's not there. You can just it's an easy calculation. You see that the last part is not there. So it's simply it's epsilon squared plus the expected value of epsilon squared. And we use a local polynomial smoothers to form residuals. So here we have the residuals y minus r hat, and here's a local polynomial smoother coming in. We prove efficiency of this residual-based estimator. And in particular, what follows from this representation is that the residual-based empirical estimator is asymptotically the same as the one based on the true errors. So you don't get worse by using an estimator, it's the same. Okay. If we know R, then we know the errors, then we can calculate the errors. Then we can use this estimator here, just the one based on the true errors, because R is a known function. However, it is in general not efficient. Does somebody have an idea why? Okay, efficiency means use all the information about the model. What do you know about the model? What do you know about capital F? About epsilons? That's the first one, and the second one? Yes, means zero.
This has to be used. Okay, it does not use this constraint, so it can be approved actually. It can be approved by adding either a correction term, an estimate of the zero, use empirical likelihood weights. And one example, so it's some illustration. For example, if you want to estimate the third moment of the error distribution, then the asymptotic variance of this estimator is that one here. And the asymptotic variance of the estimator based on the true errors is this one here. Yeah, it's simply average minus expected value, and then that's the variance. So here we have an extra term if we have the residual based estimator. That improves it. So, and you can actually calculate it explicitly if the errors are normal and we have estimated third moments, then the variance of the first one, the residual based with an estimator, computes to 6 times sigma square. And this one, based on the true errors, computes to 15 times sigma square. So that's actually quite impressive. What you lose when you forget to use the information. Yeah, it's asymptotics. It's the asymptotic variance. Okay, an alternative estimator. So it's not a very nice one, because when I was starting to think about how to estimate an optimal noise level, I asked a colleague who knew much more about non-parametric regression density estimation than I did. And she recommended to use this estimator. That was the first one that came to mind. So that's the Rice estimator, and he simply has the average sort of these neighboring responses squared. And when I saw that estimator, I thought, oh, it's too simple. That can't be the best one. And that's why how we got interested in a good estimator of the error variance. Okay, so we have seen, or we know, this sample moment, the second sample moment, is equivalent to the sample variance. Here's simply an estimator of the zero coming in, and to that U statistic here. And what does this U statistic suggest? If the epsilons are closed and R is smooth and continuous, and then the differences between Rxi and Rxj are small, so we can use the Y's instead of the epsilon. So that was the idea. And so we introduced the covariate matched U statistic. It's like this above, that is Y's, and we have some covariate matched weights, which are small if X and Xj are not close, and if they are close, they're large. Makes sense. And this estimator is clearly related to these estimators, the Rice estimators, and there are more papers which have follows the same idea. Here we have a triple instead of a pair, and then there are papers where they use D instead of 3 or 2. And we simply figured out we have to use all of them in order to get an efficient estimator. Just don't truncate it too early. That's the important part. Use all the data, not only D or a constant or a pair, and put some weight on the differences. Okay. Okay, and then we looked at completely general semi-parametric regression models, and we figured out when you're in a very, very general context, no model at all, no partially linear model, nothing, just a general semi-parametric regression model. And we figured out that if the tangent space relating to the regression function contains the constant functions, then the efficient influence function for expected value h of epsilon, in the special case, the distribution function is that. So the one we derived at the very beginning is in general the best one. Okay, now I'm wrong. Okay, some examples. For example, if we have a non-parametric regression function, then the tangent space contains the constants. If you have a partially linear model, you have the non-parametric part, so it contains the constant. If Rx theta gamma is linear with an intercept, then things are fine too. For example, when you have the very simple linear regression model, y is theta times x, plus expected value of epsilon is constant, not zero. And here's a difference. These are now the mean zero errors, but here's how the constant coming in. So if we have a linear regression, theta times x, no intercept, plus epsilon, assume means zero errors. And the line is forced through the origin. In that case, the tangent space does not contain the constants and things get a bit more difficult. Then we don't have this nice expansion anymore. Okay, so then the efficient influence function has a more complicated form, but we also derived these for several models. And these papers are actually papers about missing data. But the missing data we simply contains the full model as a special case. That's what we figured out. So there's a very general result and cover missing data and not missing data. So if you read the title, you think, oh, it's missing data. That's not interesting, but it's not true. Okay, let's go back to the fundamental expansion. Okay. Residual-based empirical distribution function, then the empirical distribution function based on the true errors. And we formulate conditions for the fundamental expansion above to hold for partially linear regression, non-parametric regression, additive regression. We consider univariate and multivariate covariates. And I will also touch all these, and later we'll talk about something with Cowell and Schick, where we derive an expansion, but not only close to one, for single index models. I think it's very interesting what we are doing there. That's why I mentioned it. And there are other papers for non-parametric heteroscedastic regression. I think everybody can read. Okay, and this is now, I think, one of our most important cited papers is in Statistics and Decisions. I guess nobody knows this journal. I think it was a German journal. They don't exist anymore. But we always were targeting a little bit too low, I think, with our papers. They asked us, so you have a paper for us. We have so little contributions, and we wrote one of our best papers for them. But anyway, the main thing in life is to be happy, not to be famous. Okay, and we consider the partially linear model. Here, V is one-dimensional, but what is actually important is chapter 2, where we derive this expansion for a general semi-parametric regression model. This is very useful for everybody who works with an error-based distribution function, residual-based in regression. So this is the expansion we derive. So what is new? Don't have here the average of the epsilons. That's only in certain cases. We have this A hat coming in, and the residual-based distribution function is here. So I write it like that one. So I add plus minus R of x, the true one, and this difference, that's now the A hat. And we have, and this A hat is some kind of perturbation which comes in because we use estimators. And A hat must be such that the above class is a Donsker class. So that's how we did it. And okay, and then so you have to look at the A hats. And we have shown in the partially linear model now that the assumptions for this expansion are satisfied if we estimate theta by a root n consistent estimator theta hat and gamma by a smoother. And so this is now a local linear smoother that's fitting a linear function with local weights, and then the intercept is the estimator of the regression function, the non-parametric part. Okay, and these are now the residuals. Everything which is unknown has a hat. Okay, so the next is a paper in statistics and probability letters. It's also interesting because here we cover the cases multivariate covariates, which makes it a bit harder. But okay, actually we know alt has a curse of dimensionality, so it's an asymptotic result. But nevertheless, it's important. Okay, a lot of people use this result from this paper because they need something which converges with this root n rate. Okay, so we showed that the expansion holds true for non-parametric regression with multivariate covariates. And the interesting thing is, I now remember, that was Hiram Powell. He approached us and said, I want this expansion for my non-parametric regression with multivariate covariates, because he had two very important papers with Kmaladze, where they have a Kmaladze goodness of fittest using a Kmaladze transform. I come back to this too. But these tests only work if you have an estimator which has this expansion, the fundamental expansion. What I think is interesting is a relationship with linear regression. Because for linear regression, when we simply have a theta, and as soon as we know theta, we know everything. So the difference f theta hat minus the empirical f t has this approximation, so the expected value of u comes in, that's the u here, times theta hat minus theta, that's the expansion. And if the theta hat is the least squares estimator, and if we have this important intercept, then the estimator uses the fact that the expected value of the errors is 0, and one can show that this part here is the same, is again the 1/n sum of the epsilon chase. So it covers lots of models, Okay, then in another paper, we look at additive regression, which is actually very useful because there's no curse of dimensionality. So we look at the partially linear additive model, which covers the non-parametric model and the linear model in special cases. For simplicity in these talks, I will let the V be two-dimensional. So the non-parametric part, the additive part, is simply the sum of two functions. Gamma 1 and gamma 2 are unknown. We only assume they are twice continuously differentiable. And we use orthogonal series estimators. And for, I think, fixed design semi-parametric regressions, there's a paper, an old one from 1990 from Randy Eubank, who was here for a very long time. And I think Jeff Hart is a co-author. And Speckman, I think, I don't know this one. Yeah, you probably do. Was he here too? No. Okay, because we're Texas A&M, I want to mention them. I think most of you know Jeff Hart, right? When did he leave? 2 years ago? Jeff Hart? Yeah, you know him, I know that. But he left not that long ago. Many of you, yes. Okay, and the idea is, and I simply like this estimator because it's so simple. We use a cosine base for gamma 1 and gamma 2. So here's the cosine base. So these are infinite many basis functions. And of course, we don't have infinite many basis functions, so we have to truncate them at some point m. So here we have this vector. Here we have this basis function for the first regression function and for the second one. And if m is large enough, and actually it can be very small, then the regression function R is well approximated by its projection on the linear space of these functions here. So we approximate it. And then is the approximation Rm is now of this form. And this approximation is now the thing that we want to estimate. And we estimate them by a least squares estimator, so a very simple estimator. So here we have the linear part, and here we have the non-parametric part. Here we have the basis functions coming in, and there's the square, and we simply minimize that. And the resulting estimator is now, okay, the C hat and the A hat comes down, and these are the estimators. Okay, then one quick remark. about additivity tests, when we have the non-parametric residual this empirical distribution function and the one in the additive model. So in the first part, you simply have a smooth function with multivariate covariates, and here we have this additive function. Then a possible test statistic would be this one here. Yeah, that's the supremum, that's a Kolmogorov-Smirnov of the difference between the non-parametric one and the additive one. But there's a problem. Does someone have an idea what the problem is? No. Oh, they are not different. That's a problem. Yes, it's the same expansion. So they cannot detect the contiguous alternatives of the form n to the -1/2 times some function. So you need some bootstrap or something if you want to use that thing. And one way out would be simply to use a different estimator for the additive part. And for example, we used in one paper a marginal integration estimator, which is derived from a polynomial smoother by integrating out all but one variable. This has a different expansion, so the difference has this approximation, which we can use for approximating the distribution. Okay, and I thought because there are no simulations, no data, you get a photo. Because people need a little break and for the attention span. Because after I left A&M in summer 2018, since then I took on two visiting positions, longer ones. The first one was in Hamburg, and this is the building where the mathematics department was. It's a really ugly building. That's what I heard from many mathematicians, that they say the mathematics buildings are always the ugliest buildings on a campus, which is often very true, like like here. Okay, so I was somewhere in the 1.5th floor. It's not a very nice view in the upper level on the Alster, but there's the administration. So I was in the former computer floor with no windows like here. Okay, so this was a Geomaticum in Hamburg. Okay, and then I was also teaching in Karlsruhe, KIT, as they call it now, Karlsruhe Institute of Technology. That's a very rich department or university. And they had a really modern building. Oh, very high tech and efficient, and with sun protection and 3 pane windows, and very, very won an architectural award even. Okay, so that was my break. Now we come to the last 12 slides. Are you ready? Yeah, I'm on time. Okay, now I come to the paper with Kaul and Schick. Okay, we looked at the non-parametric regression model, but now with a single index part coming in, which is actually an important model nowadays with many data. So, and the index here, that's called index, this needs to be estimated. Okay, so the usual assumption is for non-parametric regression that the covariate S is quasi-uniform. Quasi-uniform means it has a density that is bounded, just thinking about the uniform distribution, and bounded away from 0 on its compact support. But more distributions of the types in the uniform distribution, we call it quasi-uniform, because if you have an estimator, a non-parametric kernel estimator, for example, you need the data concentrated. They shouldn't be spread out, because then the estimator gets too bad. Okay, so we had to fight with this problem. So if theta were known and if S were quasi-uniform, we could use our results from the old papers to expand, to obtain the fundamental expansion. However, the assumption that the single index is quasi-uniform is not reasonable. Yeah, because you have a single index, it's a linear combination. The simplest linear combination is the sum of two variables. And if you have, for example, the sum of two uniform random variables, what do we get? A triangle distribution. And is it quasi-uniform? No, it's not. So we truncate it, that it's bounded away from zero in a certain interval. So that's the idea. Okay, so what we did is we estimate the single index, and then we only use the single index, is the estimated ones which are concentrated in a certain interval. Okay, and the interval is now an estimated interval, and this is an indicator. So we only use the indices that are in this interval. So here we need to find some suitable estimators which converge to some fixed interval, and you can write it in an abstract way in this form. Okay, we did not try to find the optimal estimators for the interval. So if somebody needs a project, you can think about this one. And for example, for practical applications, you could, for example, use the sample quantiles of the estimated indices to have in a compact support. Okay. Okay, now we want to assume that the density is quasi-uniform on an interval. That's an assumption. And then we assume it treats a single index model as a non-parametric regression model, and now with these estimated covariate S hat. There's a random variable coming in theta hat, and we handle that one by using discretization, as looking at values at a grid. Okay, and this is now the new error distribution function. So what we have here, this is now the residual-based error distribution function. We have the residuals, but we use only these residuals if S hat is in that compact interval. So this indicator comes in order to make things nicely. And the n is simply the number of these residuals where S hat is in the interval. So n is the sum of these indicators. And we estimate gamma hat by a local quadratic smoother. Ready? Or am I too fast now? No. Okay, that's the only new thing is not the indicators coming in order to be able to estimate this thing here nicely. Well enough to get the expansion. Okay, now our uniform expansion. So the F hat W is now the one with the indicators from the previous slide. Yeah, F hat W is this one, yeah. The new one. Wrong direction. So an F hat W minus the true distribution function is now approximated by Wn. Before we had the Cn, and the Wn is almost the Cn. Just this one comes in this weight, this additional weight, because of the indicators. And the weights have this form. W of S is the indicator that S is between L0 and U0, and L0, U0 are the intervals, limits to which I hat converges. And here we have the probability that the single index is between these two limits. And I explained that now in the next slide. Okay, recall, that was our distribution function. Now I simply multiply by 1, yeah, divided by little n times n. Then I can rewrite it. This is now 1 over little n, sum, and here with the delta hat still from here, and this is now capital N divided by n, which is, okay, now I'm jumping to the bottom. Capital N over n is simply the sum of the indicators divided by n, which is 1 over n times the sum of the indicators that S hat is in I, and this is approximately the probability that S is between L0 and U0. So that explains now the denominator, and the nominator, so the delta Hj is an indicator, and this is approximately 1 if S is between L0 and U0. So that explains this expression. Okay, now we have an influence function for this estimator. So it's the influence function we had before. Now this weight part comes in times this weight. And the asymptotic variance is simply the variance we know, the efficient variance times the expected value of this weight factor squared. Yeah, the variance where it is here squared, and this is simply this expected value of W squared, and here we simply wrote down the W squared. 1 times 1 and 0 times 0 is the same, so only here the square comes in. So this is now the constant, and here's the expected value of the indicator, which becomes the probability. So we have probability divided by squared probability, which is 1 divided by the probability, and the P0 is now the probability that the index is between L0 and U0. Okay, so we have the 1 over pi P0 coming in. Now in the variance, so we see that our estimator is not efficient because of this factor, but it's nearly efficient if P0 is close to 1. So it actually makes sense to work a little bit on these intervals, how to estimate these intervals to get a nearly efficient estimator or the best estimator. So that's the work to do. Okay, now this is called an application, but it's not really an application. Instead, we have the expansion, and we want to look at distribution-free tests about the form of the error distribution function. And so we use this expansion to get distribution-free tests. That's the application. Okay, this was our expansion. And Kaul and Kmaladze in 2009, they have 2 analyst papers where they only do Kmaladze transforms and distribution-free tests. They propose distribution-free tests for non-parametric regression based on a martingale transform of the residual-based empirical process F hat, assuming that equation 1 is satisfied. So that's very essential for the results, that this expansion is satisfied. And I'm quite proud that we are mentioned in the abstract. Nice. Okay, and this approach can be used to test F equals F0. We are almost done, no worries. For example, the null hypothesis that the errors have a normal distribution. And we also use this test to illustrate this semi-parametric additive regression model and the single index regression model. So what is the idea? Okay, here we had the approximations, this process Cn, which converges to a continuous Gaussian process C with covariance function. Here you see the Cn, so you can immediately calculate that, and you see that the n goes away. And the covariance of the weighted process is now we have the W instead of the C. Here now we have the factor 1 over P0 coming in, of course, because the variance has this additional factor 1 over P0. Okay, since capital N over N, that's P hat, consistently estimates this probability P0, our expansion yields. Okay, if I simply have here the square root of n, but now with a capital N, of this F hat W minus F, then we can rewrite it with times 1. This is now P hat times square root of n F hat W minus F. Okay, here the 1 over P0 comes in. This one estimates P0, so that cancels out. So this has the original limit, the Gaussian process, which is nice. Okay, the null hypothesis now is F has a certain parametric form. And Kaul and Kmaladze have shown that this expansion implies that the transformation of F hat, that's a Kmaladze transform, converges to this composition B circle F0 under the null hypothesis, and B is simply the standard Brownian motion, or also called Wiener process. And the transform process which they proposes is U of t here. So here you have the K coming in from Kmaladze transform. So I didn't write it down, it's in our papers, but Kn simply involves the capital F0, the density little f0, and the derivative. And as in this paper, we obtain now with these weighted empirical distribution functions that the p hat, square root of n p hat, the estimated p times u. Okay, this p hat again takes care of the 1 over p0. This tends in distribution to the composition B after F0. And now we are almost done. And the test statistic now is this one with the supremum and the absolute values. And that one converges weakly to actually B of F0 at t, but F0 is a distribution function, it's between 0 and 1, so we can write it as B of S, and the values are between 0 and 1. Which is fantastic, because that's something we know, that's something known. So we know the quantiles and everything. So here an example, some quantiles. So we have this convergence. So the test statistic is very similar to the original statistic. And I claim it's also similar to a complete case statistics, because it's the other big research area I was working on. When I tell people they can throw away the data you don't need. Because you can only construct residuals if you observe the difference y minus r of x. So, and there you get exactly the same result. So it uses only the nice cases, like a complete case statistic only uses the complete cases, which are the nice cases. And here we only use them where the S hat is well behaved. There's a single index in a certain interval. I would say that was it. Yes, that's it. Thank you.
Any questions for Ursula?
Yes, there's one. Also, may I see? In an interval I had, and we assume that the I had converges to L naught.
Assumptions about the interval, but why don't we just take intervals and like they are say approaching the whole real life, say ln un and ln goes to infinity, maybe slowly enough in logarithmic rate, so that like when you have,
I think you can do that. When you have more data, so the interval get larger. But L0 use it. I have to be careful. Yeah.
but setup you are considering, you don't have like data.
No, I think we can't do that, because even if you have something continuous like a normal distribution, you have to truncate it somewhere at the limit. Because even if you don't want the data to be densely spaced. It's a rate thing. It's a rate thing. That's all. Yeah. Infinity is very, very big. I think you don't have so many data, actually.
Is there any optimal way of choosing the length of the interval?
We didn't do that. I told you it's an open problem. It's an open problem. You can do it. No, we brought down in the abstract way the limits, but we did not discuss how to choose them You can look at the paper and make a new paper out of it. You're very welcome. I'm open for questions.
Any other question? I have one, with epsilons as differences between Weiss and the R, model R, parametric. Do you have any assumption on the smoothness of R?
Yeah, of course, but if they vary, depends on which estimator we take, we play with the assumptions. The assumption on the estimate and on the error density, of course.
Any other question? If not, let's thank Ursula.
Thank you.